Hey, so I was thinking, as I do, and I was thinking about um using metals as fuels, right? So the obvious logistic hang up and actual practical application of this is the transportation of the fuel, the building of the machines, etc., etc. Um, but from a combustion standpoint, I'm sorry, the light's too bright. Let me turn on the other salt lamp light. So from a combustion standpoint, like the engineering of the machine is something I can kind of imagine, and it's really difficult to imagine solid fuels. Right now, I'm aware that solid fuels exist in um, jets and, well, not jets probably, but rockets. Rockets will use solid fuels, I believe. And coal is about the only other solid fuel that I'm aware of. Now, is coal a good model to follow? I don't think so, but I do think that there is the potential to learn a lot from the coal industry, because they've been dealing with environmental regulations probably more than anybody, and that's where the technology is being invested. The bleeding edge technology is being invested in the dirtiest fuels. So there is stuff to learn there. And if you're looking at solid fuels, which metal oxides would qualify, that's a good place to look for equipment design. But the idea of having a coal-fired system in your house is a low temperature appliance, and it's not atomized. There's different aspects that are obviously complicating factors. Can you get these oxides hot enough where it would initiate a chain reaction? Yeah, it appears that that's exactly what happens. So you could have a self-sustaining system and be feeding it with a solid fuel, but it appears that it would have to constantly be in a dust form. The temperatures to oxidize, larger particles, like throwing a briquette of coal on a fire, would be so hot it would undoubtedly damage any equipment that was engineered to house it. In my mind, you're burning metals. It has to be in a metal container. You need to be burning those metals at the lowest possible temperature in order to minimize the damage to the metal equipment. It's just logical, right? So I was like, okay, what the existing equipment uses liquid fuel. We would obviously want a liquid fuel to maintain that. And I was like, okay, well, mixing metal with a liquid is potentially counterproductive, unless it's a ratio that makes it like the fuel is just kind of there as a thickener or something along those lines. So then I was like, okay, well, what fuels could you use? What could you use as the thickener? And I was like, well, we're already using diesel. So, and I was like, oh, I'm inventing napalm in my head. I already know this. I just forgot that, basically mixing aluminum and gasoline gives you a bootleg, a long burning gelatin that is highly corrosive to plastics and, sticky and burns a long time and is a nightmare to work with. Right? So it's like, okay, I'm imagining a napalm furnace. I'm imagining fueling your car with napalm and driving down the street burning napalm. Not because napalm is preferable, but because it's a vehicle to burn aluminum, right? And I was like, okay, well, that obviously has the physical characteristics of a bomb because of the gelatinous nature. So it kind of made me laugh for a second, but then I was like, well, hold on. Could we actually atomize napalm? And I believe that we could. If, let's say, you got, you know, 1,000 gallons of napalm delivered to your house, right, as a heating and energy source. And disregarding like the potential for any catalytic fuel cell technology that would obviously trump any combustion technology because of the chemical nature of its design. From a combustion standpoint, what would it take? And I would imagine that it would take pre-mixing your napalm fuel with an aggressive oxidizer like hydrogen peroxide. And once you mixed it with the hydrogen peroxide, it would start to rapidly decay, and you would have a short period of time to atomize it and ignite it. And in that period of time, which would be like, I'm imagining a two-pipe system, like an oxyacetylene torch, exactly like an oxyacetylene torch, except instead of acetylene, we have napalm. Instead of oxygen, we have hydrogen peroxide. And they converge, they mix together, and you atomize them as a mixed vapor cloud and ignite that mixed vapor cloud. And I think that that would be a much more energy dense process that would burn slower, longer, cleaner. It's not a carbon-free solution, but it's something that in my mind I could engineer. What I've seen as like technology that is maybe potentially available and being hidden or overhyped and suffering from logistical hang-ups that I'm not privy to. The catalytic potential of these nanoparticles far, far, far exceeds their combustion potential. But when you really, really, really dive into physics, it's almost the same thing. Like, it really depends on how you define a catalyst, I suppose. But I've seen of technologies that are being advertised that are saying that with the right, mixture, you can essentially mix some of these aluminum nanoparticles with water, expose that water to sunlight, and generate hydrogen. And that's a really great solar generator. That is amazing solar technology if you can just take some aluminum and generate hydrogen and power a fuel cell or med gas, or it probably wouldn't make the best med gas, but power a fuel cell. The thing is with all this stuff, like, you think, okay, it's going to be good. Okay. But then the logistics of a fuel cell, you need to have like super clean hydrogen, or it's going to break in a year, So there is something to be said for ultra clean, ultra energy dense combustion. I don't want to oversell the technology, because the technology has up to date not really manifested in true energy density, sustainability, and ease of access. You know, we're limited to nuclear for unlimited power, and you know, everything else is kind of falling short of basic energy needs in a lot of cases, and certainly optimistic goals for society. So the logistical hangups for combustion are really the catalytic conversion of your exhaust. And if you're ultra clean, you know, that's still an option. You know, it's not like, okay, now you've achieved 99% combustion efficiency, and by the way, you're getting a kicker with the oxidation of metal oxides that have zero emission. So relative to your BTU output, you're actually like 500% combustion efficiency, which seems impossible until you realize that those metal oxides are generating heat, but not CO2. And your CO2 is really just there as like the combustible carrier of your. So you're talking about like 500% energy efficiency, 200% energy efficiency, whatever. It seems like more than you're getting out. It's not. It's just much less CO2 per BTU because of the additional aluminum oxides that are also contributing. Now, there may be all sorts of secondary filtration systems or soot traps to capture the aluminum, you know, whatever. But it seems to me like a napalm, hydrogen peroxide, heating and well, cogen system really, power and heat is entirely possible with existing technology. I don't see how it isn't. The only question would be like, how big of a plasma, how big of an ignition source do you need? Do you need to run your ignition source constantly? You know, it's tough to say that you wouldn't be able to get usable power out of that mix that is undeniably cleaner, more energy dense than our current system. And is it perfect? No. Is it undeniably feasible? I kind of think so. A little bit goes a long way. And that might facilitate a transition to more commercial products, but you know, the downside to it is turning what is a non-flammable liquid into a very flammable liquid. You know, it's turning your oil tank into a gasoline tank. Even worse than that, you know. And there's probably additional chemical decomposition of the napalm that happens over there. I'm sure there's logistical problems, the corrosion of the storage containers, but I don't think it would be that much different than the current kind of risks analysis. You know, there's already a lot of risk in the energy sector, and to say, okay, we're going to change everything to metal oxide fuels, I don't think is rational. It might be. Maybe we get a grand reset, but the way I see things work traditionally is more like a transition. So you go from, you know, oil to a napalm fuel to plasma ion, you know, burn whatever fuel, you know, burn a rock fuel. It basically, our plasma gets bigger and bigger, and our fuel becomes less and less discriminant. But it would make sense that it would kind of snowball. And I think the mixing of aluminum and a fuel is a logical progression. And I see the immediate logistical hang up being the viscosity of that fuel. And in order to change the viscosity, pre-mixing it immediately before ignition with an oxidizer is exactly what we do with oxyacetylene. But for multiple reasons. But in this case, it would be changing the viscosity so it could be more easily atomized. But it's also the oxidizer you need. So I could imagine a system like that that would work very, very well. And I also know that these things are like militarized, you know. Even powerful hydrogen peroxide is like a big deal, you know. And making and storing napalm would certainly get people's attention from a military standpoint. But from just a fuel perspective, it is kind of like a logical transition step to a critical ion-induced nuclear society, you know, that really is ionizing whatever it wants to make whatever it wants, which is really what the process enables, you know. You can build, they can build elements and they can break elements down. And the idea of making things small so we can break them down easier is well understood. And the idea of mixing gases together so that they're more easily combustible is very well understood. And now we just need to apply that same logic to semi-solid gelatinous fuels and apply a liquid oxidizer in that regard to change the viscosity and to start the oxidation process. And I think it's something that we could do as a society that's not like, oh, let's go build the Jetsons sky or, you know, house in the sky. You know, I realize that like a space elevator isn't happening tomorrow. But this seems really like within reach of the engineering capacity of the people I know. You know, it doesn't seem like I would talk to 1,000 people in my industry and have more than half of them be like, oh, I could never do that. You know, maybe they'd be like, it makes me uncomfortable. But I think the majority of the people in my industry, it would be within their ability to work on a piece of machinery like that with some degree of comfort. The problem is, like, you know, the aggressive nature of these chemicals is dangerous. Where the current chemicals we work for, you can stick your hand in oil and not worrying about setting yourself on fire. You can stick your hand in incoming air to a system and not worry about it burning your skin because of the oxidative potential of the air we breathe. You know, as you put more energy into the system, you make the incoming components more volatile. And I think that's intrinsic, but it's within the technical reach of my industry, which is important.